Hello and welcome to an introduction to SQL Server 2017 Graph Database. My name is David Postlethwaite. I'm a database administrator for a large financial services company on the south coast of England. I've been working as a DBA for the last 7 years and I currently manage both SQL and Oracle instances. Previous to that, I was a developer using .NET, SQL, Access, FoxPro and Oracle. And way back in time, I was a Windows and a NetWare administrator. I am an occasional contributor to the blog on gethanellis.com, and if you wish to contact me, my details are on the screen. Graph Database or Graph Data is a new feature in SQL Server 2017 CTP2, and this was something completely new to me, so I started on a quest to find out as much as I could. I can't claim to be an expert yet in Graph Database, but this presentation is a culmination of my investigations so far. Some of the questions that we'll look at today: what exactly is a Graph Database? What is it used for? Does it have a specialist use, or can you use it for anything? What other companies support graph databases? And how does it work in SQL Server 2017? More importantly, will it replace traditional relational database design within the next 10 years? And finally, what is the so-called Kevin Bacon problem, sometimes called the 6 degrees of Kevin Bacon? Now, if you are hoping to learn how to make pretty pictures of your data, then I'm afraid this is not what we're talking about today. What we will be looking at is graphs that look like this, where we have a collection of related data known as nodes and relationships between them known as edges. Graph databases like this have become very popular in the last few years in areas such as supply chain management and sales data analysis. The recommendation engines that you see on places like Amazon and eBay, where it tells you that someone who bought this product also bought this other product, are using graph databases. Facebook and LinkedIn use a graph database to tell you who your first, your second and third degree friends are. In fact, anything where there is connected data can benefit from using a graph database, and this is what we're going to look at today. Our story begins in the 18th century in the town of Königsberg in Prussia on the banks of the Pregel River. The city built 7 bridges across the river, dividing the city into 4 distinct regions. And the citizens of Königsberg used to spend Sunday afternoons walking around the city, and they devised a game for themselves, and their aim was to find a way in which they could walk around the city, crossing each of the 7 bridges only once. Even though none of the citizens of Königsberg could find a route that would allow them to cross each of the bridges only once, no one could prove mathematically that it was impossible. Now, the famous mathematician Leonhard Euler was asked to find a solution, and although initially uninterested, eventually became intrigued by it. And in 1731, Euler published a paper that solved the problem, and at the same time gave birth to the subject of graph theory. Euler simplified the problem. We effectively have 4 land masses, A, B, C and D, and 7 bridges that connect those land masses. He turned the land masses into single points, which he called nodes, and he turned the bridges into lines connecting the nodes, which he called edges or vertices. If we remove the picture, what we end up with in mathematical terms is a graph, and we can draw this graph in any shape we like, but it is still the same graph. So we can restate our challenge like this. Starting at any of the 4 nodes, A, B, C or D, find a path through the graph such that you travel along each edge exactly once. In simple terms, what Euler found was the graph is traversable if all the nodes are even, i.e. there are 0 odd nodes, or exactly 2 nodes are odd and the remaining nodes are all even. And in Königsberg, all 4 nodes have an odd number of edges, therefore we don't meet the requirements, so there is no Eulerian path. So in graph theory, An Eulerian trail or path is a trail in a finite graph which visits every edge exactly once. Obviously, this being mathematics, this can be explained in a lot more complex way, but that is it in a nutshell. 2 of the 7 original bridges didn't survive World War II, and Königsberg is now part of Russia, called Kaliningrad. So now there are only 5 bridges in Kaliningrad, and if we represent the town as a graph, we get this, where we have node A has 2 degrees, node B has 2 degrees, node C has 3 degrees, and node D has 3 degrees. So in terms of graph theory, we have 2 even and just 2 odd nodes. Therefore, an Eulerian path is now possible, but it must begin on one island and end on the other. So what has our history lesson got to do with SQL Server 2017? Well, in computing terms, a graph database is one that uses nodes, edges, and properties to represent and store our data. Graph databases are great for analyzing interconnected data for finding non-obvious relationships. As I've already said, they're a natural selection for social networks and real-time recommendations. But anything where there are relationships that are difficult to represent in a traditional relational database can easily be placed into a graph database for analysis. Graph databases have been gaining momentum over the last few years with annual growth of over 300%, which probably explains why Microsoft has decided to add graph functionality to SQL Server. So in a graph database, each node represents an entity, such as a landmass, a person, a business, or even a starship. And a node will have a set of properties such as the name, the address. These are roughly the equivalent of a record in a relational database. Now, each edge represents a connection or a relationship between 2 nodes. This would normally be represented by a many-to-many table in a relational database. Each edge has a starting node and an ending node, which gives the edge direction. And edges can also have properties. In general, a node name will be a noun and an edge name will be a verb or an adjective. Once you've drawn out your graph, then meaningful patterns start to emerge, which leads to questions to query your data that you might not otherwise see in an entity relationship diagram. And Microsoft are quite late to the graph database scene. Graph database is a mature market with lots of vendors offering graph database software. Nearly all use open source NoSQL databases. And I've listed some of them on the screen here for you. Neo4j by Neo Technologies is definitely the most popular, with plenty of videos and articles on graph databases, and many of the images and information used in this presentation has come from their websites. As I've already said, graph databases have a wide variety of uses, and as people discover graph and find that it is easier to traverse and query a graph than a traditional relational database, the usage is growing. These images are taken from Neo4j and show some of the ways that their graph is being used. Most dating sites now use graph databases, as do most job websites. Twitter created its own graph database, which it has released open source as FlockDB. Neo Technologies claims to have more than 30 Global 2000 companies using its technology, including brands like Walmart, eBay, Lufthansa and Deutsche Telekom. The data from the Panama Papers that exposed the financial shenanigans of the rich and powerful was placed in a graph database for analysis. This allowed the investigators to see connections between related, unrelated people, their different addresses, shared directorships and the like, and see through the fog that many of these people use to try and hide what they are doing. And you can read more about it on the link which is on the screen now. So let's go and take a look at what Microsoft are offering us. I have some example databases that I've created, and here is my ATP tennis database that shows all the men's tennis matches played on the ATP Tour from 2000 to 2016. In SQL Server Management Studio, there is a new extension under tables called Graph Tables, where you'll see your graph tables. A blue dot indicates a node table, and the one that looks like a pair of glasses is an edge table. You can only have one graph per SQL database, and a graph can only contain node and edge tables. But you can create your node and edge tables under any schema in the database, but they all belong to one logical graph. Since nodes and edges are stored in tables, most of the operations supported on regular tables are supported on node or edge tables. But if you try to view a graph table with Management Studio 2016, then you will get an error as shown in the bottom right hand corner of that screen. Creating a node table is very straightforward. You simply add as node to the end of the create statement. SQL will add an extra column to the table called $node_ID underscore a unique automatically generated name. And this node ID column is created as an nvarchar 1000, and it stores a unique ID of each row as a JSON statement. And a default unique non-clustered index is automatically created on that node ID column. So the edge table represents a relationship between two nodes, and for the current implementation the edges are always directed. Here we simply add as edge to the end of the create statement. The edge table has three visible columns. We have the $edge underscore ID underscore automatically generated name column, and this is the unique ID to identify each row in our edge table. We'll then have a $from ID column and a $to ID column, and these will store the node IDs of the rows in the node table that we are joining together. So the first row shows the player ID 166 played in the tournament ID of 83. We have one new command in SQL which comes from the Cipher Query Language, or CQL. CQL was originally developed by Neo4j, and in 2015 it was made open source, and since then it has become the default language for virtually all graph databases. The command that SQL has adopted is the match clause that identifies the data that needs to be matched. So in this example you can see that we're selecting the tournament and the year from the players node, the played_at edge and the tournament node, with a match statement that says players who played at those tournaments, and then a filter just to limit it to Roger Federer's results. So here is the design of my ATP tennis database. All the raw data came from a website called kaggle.com, which has loads and loads of different data sets which you can use for all sorts of interesting analysis. Here is my entity relationship diagram. We have one table called tournaments with all the information about tournaments in it, another table with all the players in it, and then our many-to-many table in the middle called matches, which has the tournament ID, the winner and the loser ID, the score and the round that that match was played in. So we actually have two relationships coming from the players table. Now with an entity relationship diagram, it's not always obvious what exactly we're looking at or what exactly are the relationships between it. It's not clear, and this is where graph can become very handy. So here is my graph version of my tennis database, and here we can see that players played at tournaments, matches were scheduled at tournaments, and players won or lost matches. And this graph view just makes it so much clearer to someone looking at the database exactly what you're looking at and exactly how we could be querying it. So let's flip over to Management Studio and take a look at our database. Here I am in Management Studio 2017. If I open up my database list, here is my tennis data database, and here are my normalized tables for my tennis data. So I've got matches, players, tournaments, and this is the raw data from Kaggle called tennis data. If I open up graph tables, here you'll see all my graph tables. So my node tables are called matches, players and tournaments, and my edge tables are called lost, won, played at and scheduled at. I've had to put an N in front of all the names because even though they are graph tables, they still have to have a unique name against all the other tables in the database. So if I open up this query, which shows you how I created the normalized tables, so if we have a quick look at the tennis data, the raw data, here you'll see I've returned 46,500 rows of matches. And so for each one, I've got the location, the tournament, the year it took place in, the series, the court, the surface, the round, how many sets they had to play, the winner and the loser, the winning rank and the ranking of the two players at the time they played it, and then the score. So this one says 6-4, 6-2. This one says 6-7, 7-5, 6-3. So I simply created some tables. So I created a players table, which has got the player's name in it. Created a few indexes to help it along. A tournaments table, which has got all the information about the tournaments. And a matches table, which is our many-to-many relationship. So I've got the tournament ID in there, the winner ID and the loser ID, along with the score and the round and the best of that it was played in. A few more indexes just to keep it working. There was one row which I found had a mistake in it. The location of the tournament was spelt wrong, so I corrected that as well. And then I populated all these tables from the raw data. I'm not going to go into this in too much detail because it's not really what we are interested in doing. But here I am populating the many-to-many table with all the different results of all the different matches. And then we can start querying our data. So this query here will return all the tournaments and all the matches that were played in the ATP. One of the disadvantages of normalized data is all these inner joins. It's not very easy. It's not very easy to discern what this query is doing. Without the comment across the top, I can't tell what I am querying because the inner joins don't really explain what is happening. And they all start to look very, very similar. So this one is actually returning all the matches that Roger Federer has ever played in, which is 302. And similarly, we have more queries with inner joins, but they're very difficult to discern quickly exactly what we're looking at. Now, if we go and look at the tennis data graph queries, this is how I created my graph tables. So here we're just saying create table players with a property of player name as node. We then created the tournaments node with all the different properties I want. And then we've created the matches node with the score, the best of and the round. And then I've simply populated I've simply populated the node tables from my normalized tables. Now if we want to have a look at a node table, here is a node table, and you'll see that we have our $node ID column, and that is the unique ID of each row in the table as a JSON statement. And then over here we have all the properties of the tournaments table. So then I created my edge tables. So here's my played at edge, and I've included the ranking property in that edge so I can see what ranking the players had at the time. And along with that, I've got the scheduled at and won and lost edges. And I've simply written some queries that populate these edges. So for every edge, I need to know the node ID of the from and the to. So in this case, we're populating the played at table. So I need to know the node ID of the tournament and the node ID of each player at that tournament. And this then populates the data. Similarly down here, I've got the scheduled at edge, and for that I need to know the matches and the tournaments that those matches were played in. Similarly with the won and the lost edge, I need to know the player and the match in both cases. So these are just using standard joins to extract the information from the edge using the normalized tables, just so that we can generate some data. And if we look at an edge table, here we can see that we have our edge ID, which is our unique ID for that edge, and then we have our from ID and our to ID. So in this case we're saying that this player 61111 played at this tournament ID 3936. Now the rankings are all 0 because when I tried to use the rankings I found there's numerous mistakes in the data where players have actually changed ranking halfway through a tournament. Most likely it looks like just badly typed in, so we actually ended up with extra rows which we didn't want, so I had to give up with a ranking, unfortunately. So when we want to start querying our data, so here's a typical graph query where we're saying select the tournament of the year from the node called players, the edge called played at, and the node called tournaments. And here we're going where match players played at the tournament, and then just a filter to reduce the number of rows that we're bringing back. So we're just looking at Roger Federer's data. Now it's important that you notice that the match clause has a direction in it. So we have a dash here and an arrow, and that is important so it knows how to use the edge. Now we can write this from right to left, it doesn't make any difference. So in this match clause I've just simply said players played at tournaments. But as long as this direction works, then we'll get back exactly the same result. But if you write it the direction incorrectly, so in this case I've written it incorrectly, so in this case where match were tournaments played at players, and that doesn't work. That will return nothing because it's getting the wrong edge, the wrong node from the edge table, so it won't find any results. Here's another query. This time we're using the players node with an alias of winners. We're using the won edge and the matches node, and we're simply saying winners won matches, and that will return the 1022 matches that Roger Federer has won along with the scores. There's nothing to stop us using other T-SQL functions, such as in this case we're grouping by, so we're simply saying find the player, count the number of matches they've won, and then group by that player name. And here we're using the players node, the won edge and the matches node again, and we're simply saying where match players won matches and then grouping, and that will return our data. And as you can see, Roger Federer has won way more matches than anyone else in the last 16 years. We can make more complicated queries. So in this case, we're using quite a number of different tables. So we're saying use the players node as winners, the won edge, the matches node, the scheduled at edge, the tournaments node, the lost edge, and the players node as losers. And here we have a very long match statement. So we're saying match winners who won matches, and matches that were scheduled at tournaments, and losers who lost matches. And again, limited to just Roger Federer. And that will return the data we're looking for. Now we can shorten it slightly, so we can remove this and command from here and just have winners who won matches scheduled at tournaments and losers who lost matches, and that will return exactly the same set of data. We can't add this match clause in because it would have to fit in with the match, and you can only have a one-to-one relationship through your match clause, but it still works. There's no reason why we can't swap it around. So in this case I've said losers who lost matches scheduled at tournaments and winners who won matches, and again that produces exactly the same set of data. As long as your direction is correct, then it will work. Now here's something that doesn't work. One thing you cannot do is use the OR statement. So here I'm trying to return all the matches that Roger won or lost. But if we run this statement, we get an error message. And it basically says we can't use the match clause with an or a not. It just doesn't work. It's just not allowed at the moment. But we can get around it simply by putting brackets around our OR statement, and then this does actually return all the rows. So we can now see all the matches that Roger lost and won. Now, this particular query here shows us all the matches that Roger Federer played at Wimbledon 2016. All the matches through to the semi-finals where he lost to Raonic. Now, what I would really love to be able to do using my graph is say, what happened to Raonic in the next round? Did he win? Did he lose? Who did he play? Can we do this in one query? Well, no, we can't at the moment because SQL Server 2017 is missing a feature called polymorphism. And polymorphism allows us to find any node related to my node. And at the moment, that is not a feature which is available, which is a big drawback for SQL 2017. So currently we would have to use a CTE, where we would select the winner of that last match against Roger, and then use that to find out what happened to his conqueror. And that will return for us that in the final, Andy Murray beat Milos Raonic. So that gives you a flavour of how to use the match clause against a fairly standard looking database. Now let's go back to PowerPoint and we'll have a look at another example. A social network is one of the most common examples quoted when talking about graph databases, so I wanted to try and create one. So I've got hold of 500 unique names, and I've given the first 100 names 10 random friends using the 500 original names. And then I've written some T-SQL to try and traverse the data using traditional relational tables and then using the graph match command. And here is the entity relationship diagram for our normalized tables. And once again, when you look at this, it's not terribly obvious what we're looking at. We have a names table with the name of the person, and then we have this many-to-many table called friends with two relationships back to our normal table. But the graph is a lot simpler than this. We simply have a names table, we simply have a names node and a friend of edge, which allows us to see who is the friend of friend. Now, one of the interesting things about social media is that it's bidirectional. I can make friends with someone, but someone else can make friends with me. So we have a relationship going in both directions. But the SQL graph match command only supports one directional matching. So at the moment we would have to do two matches, one in each direction, and then union the results, and this gets really messy, so I'm not going to do that here. Let's go back to Management Studio and let's have a look at our graph database. So here is my Facebook database. I have two tables in the normalized area. I have two tables here, my names table and my friends with table, and under the graph tables I have my friends node and my friends of edge. So here's how I created the data. So I created a table called names, populated it with the 500 names that I wanted, that I downloaded off the internet. Again, added some indexes to make things run smoothly, and here is the loop that I created which goes through the first 100 names and assigns them 10 friends each from the first 500 names. I then deleted anyone who is friends with themselves, deleted any duplicates from the system, and we ended up with 989 relationships. Now, if I want to query those relationships, this is the sort of query that I would have to write in my normalized tables. And again, we're using inner joins, and it's not particularly obvious when we look at our inner joins exactly what we're joining and why. But here I am, this is me, David, and I've got 10 friends. If I scroll down, if we want to look at friends of friends, then we start having to use CTEs to get the first set of friends and then joining it to the second set of friends. If we go further down to find friends of friends, then we have to have more CTEs, and when going down even further, we end up with a very complicated set of CTEs to be able to produce our list of friends of friends of friends. But this does work, and you can see that David is friends with Betty, who is friends with Brian, and Brian is friends with Francis, and Francis is friends with all these, and Jean is friends with all these. So this is one way of doing it, but obviously when you look at this query, it's really complicated and really difficult to follow and work out what on earth is going on. So let's have a look at my graph version of this. So here I've created my friends node, and I've populated that friends node with all the names from my normalized table. And once again, our friends node looks very similar. So here we have our unique node ID and then the name of the person in question. I've then created my edge table friend of, and here I've populated my friend of table using the node IDs from the friends table and just using some inner joins to make sure I match them all up correctly so that they are the same as the normalized. And just to prove it, if I run the count on both, I get 989 relationships returned. And if I have a look at my friend of table or my friend of edge, here you'll see my unique ID as Jason, and then you'll see my friends node and the friends node again. So I'm using exactly the same node table for the from and the to. If we now want to have a look at who my friends are, here we are saying select person 2 name from friends aliased as me, friends aliased as person 2, and then the friend of edge aliased as my friends, where me is friends with person 2 and me.name is David, and that will return exactly the same 10 names that we had in our normalized. So we could write our match statement from right to left as we did previously. So here I'm saying me is friends with person 2. As long as that direction is correct, then everything is fine. Now, but because our graph is multi-directional, if we write the match statement in reverse, so person 2 is friends with me and me is David, then I get a different result. I get that Amy and Harold became friends with me. If I want to find the friends of my friend, then we write just a longer version of a match statement. So here we're saying me is friends with person 2, is friends with person 3, and then filter it to just my name. Similarly, if we look at friends of friends, we end up with a longer statement, and friends of friends of friends. Here we're going where match is me is friends with person 2, who is friends of person 3, and friends of person 4, and friends of person 5. And if we run that statement, we get back a list of all the people. So David is friends with Betty, who is friends with Brian, who is friends with Francis, who is friends with all these people. And that's exactly the same list we got as the normalized query, but this is slightly easier to follow. Now obviously writing more and more complicated queries to find friends of friends of friends of friends isn't really what we want to do. What we really want is a way to be able to traverse our nodes a certain number of times with just one simple query. And this is called transitive closure and is not yet available in SQL Server 2017. So we would need to continue to write queries like this until that particular feature is available. You can try and use a recursive CTE, but unfortunately that falls over because your first query, even though it has a match clause, always returns a standard table. It doesn't return a node table. So therefore you can't do a match statement on that result. All you can do is try and use an inner join, and that fails because you can't have an inner join with a match statement. So that doesn't work. Now there's nothing to stop us having directions pointing in different ways. So in this case I'm looking for all the friends who are common between James and myself. And here in our match clause we're saying where I am friends with person 2 and my friend is also friends with person 2. So the direction is pointing inwards from both sides to person 2. And if I run that, we will see that Betty and Jonathan are shared friends with me and James. Similarly, we could do that against everyone. And here we're saying again, so here I am, me is friends with person 2, and person 3 is friends with person 2. And this time we're going to return all the names of all the people who have shared friends. So Gregory and Joseph share a friend called Michael, as do Frank and Joseph, Joseph and Frank, Gregory and Frank. So you can see that using the match statement can make understanding queries that much bit easier than all the inner joins that we are used to seeing. That's all very well getting results back as tables, but this is a graphical thing. We want to see results visually. Now unfortunately there is no visual viewer yet within Management Studio, but we can use Power BI to do this instead. So let me move over to Power BI and I'll show you. So here's a Power BI query using one of the queries on our tennis data and on Roger Federer, and I'm using a visualization called force directed graph, and that will display our graph data in a graph. And in this particular case I've got a filter on here, so it's only showing matches that Roger won in the final, i.e. the titles that he's won. And you can see if we hover over 2004, we can see all the tournaments that he won. If we hover over 2005, similar sort of thing, and you can see that by the time 2015 comes, the number of matches that Roger was winning is much less. But as well as being able to hover over the year, there's nothing to stop us hovering over Wimbledon, and then we can start seeing when Roger won Wimbledon as well. And in this graphical way, we can obviously change the information that's there. We can start seeing patterns. We can start seeing interesting information using this. I've also got my Facebook. I've also got my Facebook graph in Power BI as well, and here you can see all the names and all the relationships. Obviously this is rather more difficult to look at, but we can start filtering our data. So if I come down here and scroll down to David, that now shows all the people who are friends with me. And if I was then to select James, We already know that James has two friends the same as I do, but this now shows it graphically. So we can now see that Jonathan and Betty are shared friends. Now if I was to select Eric as well, we can see that Eric is friends with James, who is friends with Jonathan, who is friends with me. If I add in Sandra, we've now got a loop. We've now got that. We now have an Eulerian trail possibly going round our graph. So David is friends with Jonathan, who is friends with James, who is friends with Eric, who is friends with Melissa, to Sandra, and back to David again. So using this type of graphical information allows you to start seeing patterns that you can't always see from the data, and you certainly wouldn't be able to find using all those inner joins. And this is what the power of graph databases is all about. Now this release of SQL Server Graph is definitely not ready for production systems. It lacks a number of very important features that as we have seen, but it should really be considered as a version 0.1. I guess Microsoft have added it to show customers that they are serious about graph processing, to encourage people who might be considering other vendors such as Neo4j to possibly hang on a bit longer. So as we've seen, we don't have transitive closure. How do I find a node connected to me an arbitrary number of hops away? We don't have polymorphism. How do I find any node connected to me in a graph? We're missing various functions such as shortest path. What is the shortest path between me and another particular node? We don't have any graphical view within Management Studio. We have to rely on things like Power BI at the moment. Other things that are not supported: we can't convert existing relational tables to node or edges. We can only create nodes and edges at the moment. We can't use memory optimized or system versioned or temporary tables. We can't update the node ID in an edge record. If we need to update the node ID, we'd have to create a new record and delete the old one. The view designer doesn't support graph tables. If you put your graph tables into the Management Studio view designer, it will start trying to use relational inner join type functionality. It doesn't use the match functionality. And there's no referential integrity. So you could delete a node ID and still keep the edge ID. So therefore you have your edge with nothing to connect to. So you're going to start seeing errors. So there's numerous things which are going to stop us from using graph in SQL Server successfully at the moment. So as you can see, there are numerous things which limit how we could use graph data in a production environment. So the question is, will graph replace traditional relational database design in the next 10 years? Well, over the last 30 years, relational databases have become the most common method for storing data. And whilst data was fairly small, with few relationships, these worked fine. But with the massive growth of data, relationships becoming more and more complex and diverse, and the need to be able to reshape the structure regularly, normalized tables start to become problematic. How easy is it to query a database like this one? Would all those relationships be better represented in a graph? So as the number of tables and relationships grow, then the number of joins required grows, and this can cause traditional relational databases to become slower and slower. Neo4j claim that as database and connectivity grows, their graph database will outperform a traditional relational database. They claim to be able to cope with trillions of rows, and they state that their graph database is ready and able to replace traditional databases. SQL Graph is not ready for anything like this yet, but Microsoft will add the missing functionality pretty soon, and with column store indexes, the use of R queries and the like, then I expect them to be able to match Neo4j pretty soon. But as data grows and becomes more complex, then graph will become more popular, and Microsoft want to make sure that they're capturing some of that market. So that leads to the most important question of all: what is the Kevin Bacon problem? So the 6 degrees of Kevin Bacon is again based on the 6 degrees of separation concept, which hypothesizes that any two people on Earth are 6 or fewer acquaintance links apart. Back in January 1994, Kevin Bacon said that he had worked with everyone in Hollywood, or someone has worked with them. So now movie buffs challenge each other to find the shortest path between an arbitrary actor and Kevin Bacon. And this rests on the assumption that anyone in the Hollywood film industry can be linked through their theme roles to Bacon within 6 steps. And that is it. So the game requires a group of players to try and connect any individual to Kevin Bacon as quickly as possible and as few links as possible. Now, obviously, we're not part of the Hollywood film industry. We're part of the SQL community. So maybe we should be changing this from the Kevin Bacon problem to the Brent Ozar problem. Can we find a route from any person in the SQL community to Brent Ozar in just 6 moves? There's a challenge for you. So I hope you have found this useful as an introduction to graph theory and SQL Server's use of graph database. If you have any questions, please feel free to contact me. My details are on the screen. But thank you very much for listening.